Another situation that we can solve is a coaxial cable. All right, so what a coaxial cable means is it has two wires that share an axis. So essentially, this is going to be a normal wire like so. And then around it, there's going to be a wire that's shaped like a cylindrical shell. Okay, so shaped like this. And you've seen these before. This is what you use to connect your literal cable for watching television from the wall to your television set. And there are some reasons for that that we will talk about a little bit at the end of this video. All right, so the general idea here is that the inner wire will have one charge, like this, and then the outer wire will have an opposite and equal charge like that. Okay, so we'll have a plus Q on one and a minus Q on the other. All right, so the information that we're going to need are the inner radius of the wire, so the radius of the wire, I should say, and then an outer radius, which is the radius of that surrounding cylindrical shell. Okay, so we've solved what the electric field looks like in a situation such as this using Gauss's law. So the electric field is going to be equal to lambda over 2 pi epsilon naught r. Okay, so closer to the wire it'll be larger, further away it'll be smaller. And remember, lambda is Q over L. Lambda is Q over L, so Q over 2 pi epsilon naught L r. Okay, and in order to find the delta V here, and remember we're only interested in the magnitude, so the minus sign is not going to be that interesting. We want to integrate the electric field times dr. So I'm going to integrate along a path that goes from the inner radius to the outer radius to find the potential difference between those two plates. Okay, so I'm going to integrate from the inner radius to the outer radius. Right, and so if I do that, then what I'm going to have is that I'm integrating Q over 2 pi epsilon naught Lr dr from the inner radius to the outer radius, and that leaves us with a bunch of constants. Q over 2 pi epsilon naught L, and then natural log of R outer divided by R inner. Okay, and then because we just wanted the magnitude, we should check if this is positive or negative, and then make it positive if it's negative. So R outer is bigger than R inner, and so I'm taking the natural log of a number bigger than 1, which means that this is going to come out as a positive number, which I wanted. Okay, so then to calculate the capacitance, remember Q equals C delta V. So what I want to take is C is Q over delta V. Well, now I have an expression for delta V. So Q over 2 pi epsilon naught L natural log of R naught over Ri. All right, and so the charges cancel, and to write this in a slightly nicer way, I'll get 2 pi epsilon naught L over natural log of R0 over Ri. I can get rid of the absolute values because radii are always positive. Okay, so the capacitance then for a coaxial cable follows this expression. And notice it depends on the length. So sometimes people will express this as a capacitance per length. So C over L is 2 pi epsilon naught over natural log of R0 over Ri. All right, so one of the things that is really nice about a coaxial cable is that the electric field outside of the cable is 0. All right. So, in the case of something like a television cable where you're trying to transmit a lot of data, that means that it will prevent interference from other wires, and it will also not affect other things that are nearby. Later on, we'll see that even if there's an electric current through the cable, which there often will be the case, that will also not have any magnetic effects outside the cable. So coaxial cables are really nice for preventing interference between different things. Um, but the downside is that, as you can see here from our calculation, there is a capacitance associated with the cable. So for the most part, coaxial cables solve more problems than they introduce. But if you're going to design a system using coaxial cables, you'll need to take into account the fact that they are essentially a capacitor and they can affect other things. So this is the sort of thing that if you're going into electrical engineering, you will have to spend some time thinking about and solving in various contexts, quite likely.